Weikuan Yu from Auburn University. He's an associate professor in the Department of Computer Science, Software Engineering. He directs a parallel architecture and system laboratory with a cutting-edge 40 teraflop, 100-node heterogeneous GPU plus CPU computer cluster. Yu has researched interest on big data, high-performance computing, computer architecture, file and storage systems, and interdisciplinary research on climate modeling and computational biology. His research has been sponsored by NASA, NSF, DOE, ORNL, LLNL, Intel, Mellanox, NVIDIA, Solar Flare. Did Disney support you? Right on. Weikuan is a very accomplished guy. On the other hand, it says here that Omkar Kulkarni works for Intel. No, that's cool. I mean, you know, ladies and gentlemen, Omkar.
Yeah, I just forgot to send in my bio. So I'm a software engineer with the High Performance Data Division at Intel, which is basically the Lustre org. We saw in the previous talk that you know, one of the problems with running Hadoop on top of Lustre is that Hadoop has a very different model of I/O than Lustre does. It's basically like big data analytics, and one of the things about analytics is that you want to minimize the movement of data, and with Lustre, it's, you know, the storage clusters are usually remote, and all the client nodes are, you know, they have to pull the data in order to perform any processing on it. So one of the projects we actually undertook, you know, in collaboration with Lawrence Livermore and Auburn University was, it's called analysis shipping, and Eric actually explained some of it with a very fancy graphic in his presentation yesterday. So I'll skip this part because it's MapReduce, and, you know, Ziki already explained most of this. Yarn is essentially the new framework for MapReduce from Apache. It's also known as MapReduce version 2. What they did was they basically yanked out all the components of MapReduce and made them loosely coupled, and, you know, which can run standalone. Yarn stands for yet another resource negotiator. So basically they try to make it something like a generic resource scheduling framework. And it has other components, which is MapReduce, which basically runs as an application on Yarn. And then you have the distributed file system, which is HDFS. And that, you know, in our project, that, you know, HDFS basically gets eliminated because we are using Lustre. So, you know, this is basically how, you know, Lustre file systems are configured as, you know, separate storage clusters. And what we wanted to do with this project was to actually run the mappers and the maps and the reduces on top of the OSS nodes, so that, you know, all the analytics happens in, you know, in situ. What's that? Well, the OSTs are attached to the OSSs, right? And
C2 means on the compute nodes to me.
Okay, so maybe I used the wrong term. Basically, what I meant was we want to achieve maximum locality of all the analytics. The approach we took was, you know, which is very similar. And there is actually another problem with using Lustre as a file system. Normally in HPC clusters, the compute nodes don't have any, you know, or hardly have any local disk capacity. And when using HDFS, Hadoop assumes that there are locally attached disks, and Hadoop, you know, HDFS essentially logically splits the local capacity into two sections. One is the HDFS section, which is used as a block store by HDFS, and the remaining sort of capacity is used as, you know, temporary scratch space for, you know, intermediate map and reduce data. With Lustre, we don't have that. We essentially have just one single view of the file system, which is mounted locally. So in order to resolve that, we basically try to ship the analysis out from the compute nodes to the actual OSS storage nodes by providing information on where the stripe data is located to the scheduling framework. We try to convey exactly the IP addresses of all the OSS nodes so that the scheduling framework can launch the mappers and reducers wherever the data is located. Okay, so I'll actually call Weikuan to take you further through this. He and his students have actually implemented the whole thing, and
oh, well, Omkar had a short bio. I didn't intend to have such a long introduction, but before I start, I would like to give special thanks to my collaborators, Omkar, Brian, Robin Goldstone, and Eric Burden. Well, I didn't list Eric there, but Robin and Eric are the main pushers behind this project. I really appreciate their support. Okay, so since Doc Tao from Intel introduced a lot about Yang and running Yang with Lustre, so we will skip an introduction on this analytics shipping. As Omkar mentioned, this is actually the brainchild of Eric Burden, and we'll just go directly into what we would do. So in order to realize analytics shipping in this HPC environment, we divide analytics shipping into three small objectives. In that three small objectives, basically, first of all, we want to segregate analytics workload and the storage functionality from Lustre server. The point is, when we ship analytics from computer node down to storage node, so we want to minimize the perturbation caused by analytics workload to the storage functionality. So here, if I can help with that previous question, what we mean by in situ. Here, in situ we mean that we put analytics in situ within the storage node, not on the computer node.
This is not in situ that everybody knows, which is the visualization.
In situ really depends on where your data is. So we consider this in situ when data is already generated and stored back there. So you do have argument. I'm not trying to disagree with you, but we just say what we define here in terms of our in situ. So, and then once we were able to separate the analytics and the storage functionality, we want to have a coordinated data placement and task scheduling framework so that we can achieve or avoid the mismatch between the HPC configuration and the data-centric HDFS configuration. And finally, the third technique is try to improve intermediate data organization. Okay, so, well, let's look at the very first one, how we separate the analytics functionality and the storage functionality and how we evaluate them. So we use a KVM as a virtual machine technique, create an instance on the storage node. And then, but we will put a Lustre servers on the physical machines. So this way we hope that all analytics functionality will be localized and constrained within the virtual machine. And as much as we can do to eliminate this perturbation to storage functionality. And there is an option, well, where you want to place the Yang intermediate data. So we will take a look at that later on. First of all, let's take a look at the performance between running Yang in a virtual environment and running Yang on the physical machines. As you can see, look at first the two bars to your left, and there is a 62.6% difference. That's the performance loss caused by using KVM. And besides this comparison, we also want to check, say that when we ship analytics to the storage node, and in the HPC environment, there could be concurrent I/O functionality from scientific applications. So we run IOR programs on 6 other machines, consider they are I/O traffic caused by scientific applications. As you can see, the last 2 bars to your right showing that the concurrent I/O activities doesn't cause too much performance loss in terms of analytics functionality. Okay, now once we identify there is a KVM overhead that huge and what we can do. And we did 2 small tricks to look at how can we reduce the KVM overhead. And the 2 things we did is, number 1, increase the number of cores from 4 to 6, because in the previous test, we used 4 cores for every young job. Okay, then we also increased memory node. If you compare the first 2 bars, okay, if you compare the bars from the second to the third, when we increase the number of cores from 4 to 6, then we say the performance overhead is no longer as huge. Earlier it was 2.6, now it's reduced down to 31. And between the last 2 bars, the increase in memory doesn't help as much, okay? So as most of you know here in this audience, that within Lustre servers, Lustre server functionality requires a lot of memory. So if we put Young's analytics workload into the storage server, we wonder what kind of perturbation the memory consumption would cause to Lustre functionality. So we want to make sure that running Young along with Lustre OSS and OSD doesn't take too much memory away from those. So we profile the memory utilization, as you can see from this figure. And if we measure its memory consumption for the Young and for Lustre's local file system, and we do see there is a fluctuation as the Young's functionality changes. So, but if we put all this in a virtual machine environment, then that memory consumption is eliminated. But by the way, this experiment is done in the physical environment. It's no longer running Young on a virtual machine, but we want to at least first exhibit a problem, then we show that separate Young functionality in the virtual machine can eliminate the problem. Okay, so now I have shown you the utilization of virtual machine to do analytics shipping. Then the next question, or the next objective on my agenda is trying to say how the data placement and task scheduler would be affected. So the first one is about placement of intermediate data. As many of you know that Young jobs create a big amount of intermediate data. Well, in the HPC environment, you no longer have intermediate or local disk to hold that intermediate data. So naturally, you want to place intermediate data to Lustre. So we compared 2 cases. When you run Young on Lustre, where you put intermediate data, the local disk or Lustre. So as you can see here, we run 2 different benchmarks, and there is indeed a performance overhead caused by putting the intermediate data on the Lustre. Okay, so the performance loss can vary depending on whether your benchmark is data intensive or not. For TeraSort, which can have a very large amount of intermediate data, the performance loss can be 35%, but for PageRun, it can be 17%. Okay, now we have seen the impact of data placement. Now we want to see the impact of task scheduling. So normally, if you run Young or Hadoop on HDFS, they automatically try to schedule the tasks to where the data is located. But with Lustre, this may not be the default case. So, and I bring to your attention this complex figure. And well, my student was trying to show me his deep understanding of the code stack, but it really doesn't need to be so complex. But I want to give you a high-level picture. So when a client submits a job and the resource manager takes over, receives the job and the location of the file, and we can extract the location of Lustre straps by making a query to Lustre metadata. So then we will send the list of strap information to the MR application master. So from that application master, we can ask each and every node manager saying, for the first strap, where it is, you should launch the first map task. So that gives you an idea how we achieve data locality when we schedule tasks. So depending on how you place intermediate data, on Lustre or on local disk, and you have two choices. Depending on how you schedule tasks, and you want to schedule tasks with locality or without locality, you have also two choices. So 2 by 2, together you have 4 different cases. So we compare 4 different cases in terms of their data locality as well as their performance. So we measure the 4 cases using Lustre 2.5. So this slide shows the comparison in terms of the locality of map tasks. Essentially, we measure the number of map tasks who can achieve locality by running the map tasks with the data on a local node. So as you can see, with optimized task scheduling, well, we can achieve very high locality for the 2 cases. But for the other 2 cases that we don't optimize the locality, then the position of a task and the position of last steps can vary a lot. So oftentimes they don't match with each other. Well, however, the good locality of the 2 cases doesn't translate to good performance. So among the 4 cases, so the putting data on a local disk using the original task placement still has the best performance. So we wonder what is going on. Okay, so and to the final part of the presentation, I want to bring to you how we try to improve or optimize the cases or performance trend we have found. So looking at this slide over here, I want to bring to your attention the data flow in the original yarn when it is running on Hadoop distributed file system. So as you can see, or as many of the previous speakers have discussed, so when a map task is launched, it will read data from HDFS in the default environment, and the data will be analyzed through map task and stored on a local disk. And in between, the data will be spilled to disk and read it back, and finally merged as map output. And when reduced tasks are launched, and then they will fetch data from the map output, and in between they also spill and merge, and until all map output files are fetched and merged together. So the reduced task will go through a reduce function and store the final data into HDFS. So in the default case, when you run yarn on top of HDFS, you actually make use of both Hadoop distributed file system as well as local disk. But in the last environment, you no longer have that local disk in the picture. So what do? And this shows that if you don't do any optimization when you want to run yarn on Lustre, so here's the case of data flow. We again will read data from Lustre, but by the time the map task generates output, and they will spill and merge, but all happens within Lustre. When map tasks are done and reduced tasks kick off, and they will read map output from Lustre again and spill and merge. Every I/O activity will again happen within Lustre. As you can see, many of these can be repetitive I/O, can be very small segments of I/O, and which is not what Lustre is good at. So our point is, how can we make this case better? So what we have done is showing you how to achieve locality. So in the initial phase, reading input from Lustre and writing data to the Lustre. So we will try to figure out where to place the data, where to read the data. So there we achieve the best locality we can. But in the middle part is where the small repetitive I/O is coming from. So our optimization is trying to keep much of the merging and fetching above Lustre. And we also try to do that in a small unit manner so that we don't cause a lot of memory pressure and we do not have to spill as frequently. And this way we can reduce network contention and reduce the metadata overhead cost to Lustre. So I don't want to go into too much detail about exactly what we have done, but we're still working on an essay paper. So this slide was produced 3 weeks ago. So as you can imagine, things can happen in the last few weeks. So a lot of things have changed. But as an initial set of results, we compared 2 different cases, running yarn on original Lustre and running yarn on Lustre with our optimizations. As you can see, and across TeraSort executions from 8 gigabytes all the way to 32 gigabytes, and we see consistent improvement with our optimizations. And things are actually looking even better with the latest results, but this was 2 or 3 weeks ago's work. And finally, in summary, we have explored the design of analytics shipping by integrating Lustre and Hadoop together. We have shown a performance evaluation for all the issues we are concerned with, and we have shared with you the performance. And we also have conducted a few initial optimizations, and the optimization looks like very beneficial. So it's time for me to take questions, but I want to show you our acknowledgement to our sponsors and the students that actually did the work. Thank you. Please. Please, yeah.
Your KVM is on the OSS, and it mounts Lustre. How local is the data? I mean, the data could come from another OSS, so you have to ship it over the network as well. Is there any shortcut you use to limit to particular OSTs which are on the same OSS?
There's echo sound from your microphone. I just couldn't hear anything. Okay.
Works better now?
Yeah, works better.
So your data is coming from various OSSs to the KVM, which is running on one particular OSS. So the data is not actually local to that OSS, is it? Do you have a shortcut to access only data from OSTs which are located on the OSS on which the KVM is running?
There's a communication issue. So if I can try to reinterpret what you said, I'm not sure exactly what I catched what you mean, okay? So you're trying to say that the data is with OSS. The data are always with OST, so OST will be mapped with OSS. So then when we read them in, if the task is reading input from the local OST, then it'll be local. But the last step may or may not be on the local OST.
So that's the thing. What we do is we arrange the striping in such a manner on Lustre. That's at the point of staging the data. At that point, we arrange the striping in such a manner that the stripe sizes are large enough so that each mapper can read. The information of the stripe is already given to the scheduler, and the scheduler will then see where that stripe is located and launch the task on that OSS. Does that answer the question? Thank you.
I saw on one of the slides you had shown you basically looked at the overhead, or how the overhead of KVM changes when you were running IOR, and that was a very small difference, so IOR didn't affect the KVM much. But what about the other way? How much is throughput like IOR affected with the KVM there versus not, or does it not affect it much at all?
Well, IOR were running on 6 other machines. So your question is, what is the impact our KVM would cause on IOR?
Yes.
We did not measure that. Thank you. Very good.
I have a question. So
Please.
A few slides ago, you showed local versus remote performance differences, and they look the same?
They look not the same, but with very little variations. So essentially, our optimization didn't provide in the desired improvement.
What I'm taking out of that is that locality doesn't matter. In other words, if the performance is the same, whether the data is local or whether it's not, then why does locality matter at all?
The locality matters, but to a very small extent. And the largest improvement we have observed is 7 to 10%. So also it depends on how much overhead the other components would cause to the entire execution. So if the portion of improvement is anyway small, and the other portions can cost very long, so the total percentage will be even smaller. So, but the best benefit we have observed is 7 to 10%. It's not significant enough, so consistently. Any more? Okay. Thank you.
Thank you, Weikuan.